So today we're going to talk, since we're talking about transition metals and catalysis and asymmetric catalysis, we've been talking about that too. Today we're going to talk about asymmetric hydrogenation, and so I'm going to share my screen, and I'll have this uploaded today along with some other, a couple of other notes and a couple of seminal articles to go along with it. So um, let's see. Right. So with hydrogenation, you're basically adding H2 across a alkene. It also works on carbonyls. Ryoji Noyori actually won a Nobel Prize for his work dealing with asymmetric hydrogenation of carbonyl bonds. So we're going to talk about that later. But if you take just an alkene, transition metal catalyst, and hydrogen gas, you can do uh, hydrogenation of the alkene. You can see here where you can hydrogenate here, or here and here, like this, right? I know this is not a chiral center, but it's just to show uh, the stereochemistry, right? This this carbon right here, if there was another atom or something else there, then it would be chiral. But it's just to show the stereochemistry and to show that both hydrogens add to the same face, right? So it's always syn addition across that double bond. So they're either going to both add to the front face or they're both going to add to the back face. When you think about alkenes in particular, they are planar. So you're gonna have that facial selectivity where either something's gonna add to the front face or back face or top face or bottom face, however you want to, whatever the transition state dictates. Um, so it's the catalyst that determines the favorite stereoisomer. We talked about this when we talked about asymmetric catalysis, right? The catalyst creates an environment around the substrate where that favors addition of your nucleophile or whatever you're adding from one side relative to the other side, and then you have these two competing transition states. Obviously, the one that's lowest in energy is going to be the transition state that dictates the outcome of the reaction. All right, and then the thing about hydrogenation that is special is that it has multiple industrial applications, and I think that's why the Nobel Prize was actually split that year between two chemists for that. The application of this technology to an industrial setting by scaling up these reactions way up so that you can apply it in a pharmaceutical setting, in a agrochemical setting, just different settings like that. And again, this technology, this reduction technology, is actually amenable to both alkenes as well as carbonyls, as you can see here. So here you actually can hydrogenate a CO bond, CO double bond, and get out two chiral products, right? Which one predominates is going to depend on the catalyst, and it's going to depend on a lot of things. All right. Um, so here's a general mechanism for hydrogenation, right? You start with your catalyst. This is the catalytic cycle for that. You start with your catalyst, right? You add hydrogen across it, and like so, and then that metal hydride or metal dihydride can then coordinate an alkene and then do what's called migratory insertion, right? Where a pair of electrons from the metal hydride bond is transferred here, so you get a new bond to hydrogen, and then a pair of electrons from the pi bond is transferred to the metal, so you have a metal carbon bond here. And then after that, you just simply do reductive elimination, where this carbon and this hydrogen end up bonded together. So that's the generic catalytic cycle for hydrogenation. Now there are other ways to make metal hydrides, and this is kind of like a paradigm to show how, like, other methods to get to a metal hydride, right? You can see here, you can do transmetallation between a metal and then a metal hydride like tin, boron, or silicon. You do a transmetallation and you end up with a hydride here on this metal, as well as the loss of HX, which is not shown, but it's here, right? Um, and then you can also do like the traditional method where you just stir the metal in the presence of hydrogen gas, right? And I don't know if this is has been clarified or not, but I'll clarify it now. So when you add in, when you're doing a hydrogenation, right, you're doing the reaction in a sealed vessel under pressure, right, of hydrogen gas. So you just, I've done this like the rudimentary way where you take a balloon, you fill it with hydrogen. Uh, basically, it's a really crude method for doing it. What we used to do is take a syringe, a plastic syringe, cut the end off, put a balloon over it, and duct tape it, or use electrical tape to seal it up, and then attach that to a hose that's attached to a hydrogen tank. Fill that balloon up, put a needle on the end of it, and then cap your reaction vessel with a septum and put the needle down in there, and it the flush out the oxygen, right? So put an exit needle in to flush out the oxygen, and then take that out and run that under pressure of hydrogen, right? There are much more sophisticated ways of doing it. You can run the reaction in like a bomb calorimeter or something like that, and that works too. But that's the traditional way to just do oxidative addition. You could also protonate a negatively charged metal with a proton source and get to that metal hydride, right? And here you can do beta elimination. We've seen that before. Beta hydride elimination, where the adjacent carbon to the metal is the hydrogen is actually removed from that. So you can do beta hydride elimination to get here. Um, Beta elimination, which is here to get here. And you can even do, you can take like a uh, metal carbonyl species and rearrange that to get a metal hydride to get here. Right. So there's a lot of ways to get to that, but the traditional method is probably the most widely used. I've actually used this method as well, where when we did reductive aldol chemistry, we started with a silane that transferred a hydrogen to the metal, and then the metal inserted into uh, a double bond that was conjugated with the ester. So there's a lot of ways to get to that metal hydride. These are the seminal catalysts. The Wilkinson catalyst is here. It's a rhodium uh, phosphine catalyst, and it is a fairly efficient catalyst. And I put the references down here, so if you want to go and grab those and check that out, you can. So Wilkinson's catalyst, Crabtree's catalyst is here. It's an iridium, a cationic iridium-based catalyst. Um, and then Nayori developed this chiral catalyst, uh, this ruthenium binap catalyst for hydrogenation. And then Knowles, this is the Knowles catalyst. It's like a BiPAMP. I think that's the abbreviation for that. But it's a rhodium catalyst, similar to the Nayori catalyst, and they actually split the Nobel Prize in chemistry for their work in asymmetric hydrogenation. So yeah, the Knowles catalyst is here. That dates all the way back to 1975. So this technology has been developed over multiple decades to get to where it is now. But the Wilkinson and Crabtree catalysts were just simple hydrogenation catalysts. And you can see here for the Wilkinson catalyst, uh, it's actually a monohydride. We're going to talk about that in a second. It's a monohydride catalyst, right? Where you start here and then you add in H2. But this is a very rarely used, this monohydride, because you get alkene isomerization, right? And so you don't want that. So here, the Wilkinson catalyst is a chloride, that's shown here, and it's a dihydride catalyst. This is a precursor to that, but this is a dihydride catalyst, and it's fairly efficient. You can see the reactivity, the scope down here. Uh, Cyclohexanes and monosubstituted alkenes react about the same. Uh, 1,1 disubstituted alkenes react pretty rapidly. Cis alkenes and then trans alkenes. So cis alkenes disubstituted react faster than trans, and a substituted cyclohexane is the slowest out of all of them, right? A trisubstituted and tetrasubstituted alkenes don't react. Why do you think? Let's go back to here. Why would a cis alkene uh, react faster than a trans alkene? Based on the mechanism. And do you think it's a steric argument or an electronic argument?
It looks to me like it might be a steric argument.
Okay. So do you what is the uh sterically, what do you think is the issue? If I took a if this was a trans alkene, what do you think would be the issue? I mean, one of the main steps is actually having the alkene to coordinate to the metal. So what do you think the issue is sterically? I agree with you, by the way.
I mean, just looks like it's gonna be some interaction. The mother group is on the other side. Sorry, my dog is acting up. It
Okay.
yeah, it may push it away. Just
Yeah.
reduce the bonding.
Yeah. So the methyl group that's here, if it was in a trans position, it's going to actually affect how that alkene can coordinate. Right? It won't coordinate as tightly as it does in the cis, where both methyl groups are kind of away from the metal center. So yeah, you're right about that. And that's those are the kind of things that we have to think about when we look at reactions like this. So the cis is more reactive than the trans, and we can see why, right? The trans is gonna seem sterically bulkier, right, to the metal, and so it won't coordinate as well. All right, so the Crabtree catalyst is about 100 times more reactive than Wilkinson's catalyst, and you typically see this uh, with cationic species, right? So this is the Crabtree catalyst. It's a 16 electron complex, and you typically see this with cationic species that they're slightly more reactive, right? So when you treat this with hydrogen gas in a non-coordinating solvent, which is important, um, the solvent actually does play a role in several of these hydrogenation mechanisms. A couple of the ones that we're going to see coming up in the talk, but the solvent actually displaces ligands and things like that. So if it's a non-coordinating solvent, it goes through a dihydride mechanism, and it's about 100 times more reactive than Wilkinson's. Uh, you can see right here for just a typical terminal alkene, Wilkinson's catalyst gives you about 650 turnovers per hour, and Crabtree's catalyst gives you about 6,400 turnovers per hour. And again, turnover simply means, let me go back to here, how many times the metal goes through this cycle, right? So when it goes through one time, that's a turnover, right? So you're getting with the Crabtree catalyst 6,400 turnovers per hour, all right? Um, Take a cyclic alkene like cyclohexene, all right, it's about 4,500 turnovers per hour compared to 700 turnovers per hour for the Wilkinson's catalyst. And then even with the tetrasubstituted alkene, right? Remember, Wilkinson's catalyst does not work on tetrasubstituted or trisubstituted alkenes, right? But the Crabtree catalyst can actually uh, hydrogenate a tetrasubstituted alkene and give you about 4,000 turnovers um, per hour, which is great. And these are some examples, right? These are not asymmetric examples. These are examples of how the catalyst can be selectively used to hydrogenate alkenes. So you can see right here, you got 3 alkenes in this molecule, but only one gets hydrogenated with a Wilkinson's catalyst, and you get about 90% yield. This was published in 2000 in Organic Letters. Um, but it didn't touch the other alkenes, right? Uh, Same here, you can see with Crabtree's catalyst, this is a pretty bulky 7-member bicyclic system. And with 4% Crabtree's catalyst, you can hydrogenate this bond in up to 94% yield. Right. In the bottom example, again, this is an example of selectivity. You have 2 alkenes that are plausible um, substrates, and then you have your Wilkinson's catalyst here, and only the terminal alkene gets hydrogenated. And then the disubstituted or trisubstituted alkene in here doesn't, but we know that with Wilkinson's, that's a strategic application because we know that Wilkinson's catalyst won't touch that. But the Crabtree catalyst probably would hydrogenate both alkenes. So again, that's um, another place where we can strategically apply reactions to give us what we need, right? If we want this product with the alkene intact, then we have to apply a method that won't touch that alkene. So you also have what we call directed hydrogenations, and this is kind of a entree into asymmetric hydrogenations, right? Because if it's directed, kind of like when we talked about the sharpless epoxidation on allylic and homoallylic alcohols, how the sharpless is actually directed by uh, an alcohol. The oxidation part is directed by an alcohol. So if you have a chiral alcohol, then you necessarily are going to get a chiral product because the alcohol itself can actually act as a Lewis base and direct the metal catalyst to the alkene, right? So here you can start with a metal with a cyclooctadiene ligand, a cationic metal with a BF4 counter ion or PF6. It just depends on which catalyst you use. These are typical for the hydrogenation of allylic and homoallylic alcohols, right? And so here again, here's where we can see that solvent come into play. If it's a coordinating solvent like THF or something like that, right? You can actually displace the cyclooctadiene ligand, the COD ligand, and get this metal solvent complex, right? That's fairly prevalent with transition metal catalysts that use that COD ligand. It can be displaced by solvent. So you have this solvent complex, and then that is what does your hydrogenation, right? So you have the solvent, metal solvent complex, and then you add in your homoallylic alcohol, and you can see again right away the alcohol displaces one solvent molecule, and then coordination to the alkene displaces the other. So now you have this complex, and it's in competition with this metal alkene complex right here, right? And it's all cationic. Then when you add in your hydrogen and hydrogenate the metal, this is what the complex looks like, right? If this is the favorite complex, then it's going to react faster and go through the addition of hydrogen, followed by migratory insertion and then reductive elimination. Um, and if you can have this doesn't have to be an alcohol. It can be other Lewis bases. It can be an amine. It can be a sulfur. As long as it's Lewis basic and it can coordinate to that metal, right? So these are your two transition, well, not transition states, but two competing complexes uh, that are plausible. And if we take this one, this is the one that leads to the main product here, where the hydrogen is directed uh, from the opposite side of where the OH is, right? So we're here and we end up doing, again, insertion followed by reductive elimination. So this hydrogen ends up here and we end up with this product where the methyl group is on the same side as oxygen, which means that the hydrogen came from the back side of that alkene. All right. Any questions about anything so far? All right.
Not so far.
All right. Um, so let's move on and look at these asymmetric hydrogenations. And this was published in Organic Process Research and Development 2009. Right. This is a huge discovery, a huge accomplishment, where you can take hydrogen gas and triethylamine and methanol and your catalyst and hydrogenate this alkene. Notice it is similar in structure to a tri-substituted alkene, but it also contains functional groups that are relevant, right? And sometimes in the case of certain types of functional groups, they are biologically relevant. So it just depends on what your start material is. But note it, look at the scale, right? You're doing 3 kilograms or almost 4 kilograms of this start material, right? And 13 liters of methanol. So this is a huge reaction vessel. And then you're able to generate 3.32 kilograms, so by about 86% yield of the hydrogenated product, where the hydrogen added here, right to the front face. Um, 86% yield and 97% EE. That is literally the holy grail of asymmetric catalysis, right? High enantioselectivity, selectivity, high yield, very low catalyst loading. Look at the amount of catalyst that's used, 0.005 mole percent of catalyst. So still a lot. 74 grams is a lot, but in the grand scheme, it's only 0.005%. Uh, and then you have, especially compared to 3.9 kilograms. That's quite a small amount of catalyst. But this is the Noyori ruthenium binap catalyst, and you can see the binap, the chirality comes from here, right? It's axial chirality, where you have this part of the ring is kind of, if you think about putting your two thumbs together and your other four fingers are kind of like a paddle, right? One paddle is up and one paddle is back. So this paddle, this backside is coming out of the page, right? And then for this paddle, the front side will be coming out of the page. And you can see here in 2001, Knowles, who is a process chemist, an industrial chemist, split the Nobel Prize in chemistry with Noyori for this technology, this asymmetric hydrogenation technology. These guys are highly celebrated chemists in this area. And again, it kind of points to something that a lot of times we don't talk about, and that is that many times a scientist, a chemist, or whoever is going to find a niche area and they're going to work that, they're going to milk it to death, right? So this asymmetric hydrogenation, if you go back to those seminal papers from the 70s and early 80s, you'll see you start out with an idea and you take that idea and you just find other places where you can apply it. That's how a lot of scientists, a lot of chemists especially, build their careers. They build it based on one or two reactions that they perfected and applied to multiple situations and multiple substrates. You always have a target in mind when you're developing a method or developing new technology. You always got to have a target in mind. So to be able to scale these reactions up and use this low of a catalyst loading is a monumental feat, and maintain enantioselectivity selectivity and maintain high turnover and high yield. That's a monumental feat. These are some of the the ligands used for asymmetric catalysis, and you can see the phosphine is that's going to be my coordinating uh, functional group to coordinate to my metal and build that scaffold around the metal that kind of forces uh, substrates to come in and bind a certain way on a certain face, right? That's what all of these ligands are designed for that, right? Chirophos, Duphos, methyl Duphos, that's all. And then these ligands are modular, right? Just like there is a methyl a methyl Duphos, right? You can easily consider converting the methyl into isopropyl or tert butyl to put more bulk around the metallic center and give you more steric interference and potentially increase your enantiomer selectivity, right? Same with all of these like tane phos, sin phos, different um, all these different ligands with different chirality and different chiral elements. Uh, they really change the outcome of your reaction, the selectivity wise. Like something like Fame Foss or Josie Foss. I've actually worked with a lot of these ligands as a graduate student because the my advisor into he was an organometallic chemist, but he was also into asymmetric catalysis. So we used a lot of these ligands. They're not cheap either, but all of them are now commercially available. Back then, we used to make. I don't see they don't have any box. Well, they have a box derivative right here, C1 symmetric box derivative. But back then, we used to actually make bisoxazolines ourselves, right? The technology was published, but it wasn't. They weren't. A lot of them weren't commercially available, so we used to make our own derivatives of these bisoxazolines. Um, so yeah, so here with asymmetric hydrogenation, initially, uh, again, you have this is for the Noyori catalyst, which can actually hydrogenate a carbonyl or it can hydrogenate an alkene. But here, the initial results were with the alkene. So you have some coordinating element in that molecule. Remember when we talked about asymmetric catalysis, one of the key features that had to be present is something that can actually coordinate to the metal. You have to have some Lewis basic functional group that can chelate and grab onto that metal, right? So you start out here, you have a metal solvent complex, and then when you expose it to your substrate, you actually generate two diastereomeric complexes, right, as intermediates. They're diastereomers because of the BINAP ligand, right? The BINAP ligand has set stereochemistry, but the way that this binds, right, makes them diastereomeric. So you can see the carbonyl can bind to this side, or it can be bound to this side in the metal, right? And notice this is the minor uh, diastereomer, right? This complex is the minor complex, and this is the major complex, right? But because there's more than one step in the mechanism, you can have a energetically unfavorable complex. But if there's another step that has to happen, that's what the Curtin-Hammett uh, postulate says that if you have two competing diastereomeric transition complexes, two competing intermediates, the one of them is going to react faster based on the energetic barrier to get to the next step. So here, if the activation energy to go from here to here is lower, then it's going to react faster than this, even though this is your major diastereomer. And so you can see here, this is slow compared to that. So when you add the hydrogen in and you actually hydrogenate your metal, right, the minor diastereomer reacts faster. So you end up here and you get 98% of this, right, greater than 98%. And here, after you do your insertion and your reductive elimination, this is your hydrogenation product, the R isomer, right? And greater than 98%, and then less than 2% for the S isomer, right? But these complexes, these diastereomeric complexes are equilibrating, right? So you can go from here back to here, and then you can bind a different way to get to here, right? And those are in equilibrium with one another, right? But once you get here, the step to get to hydrogenate your metal, if that's faster for this one, then that's the pathway that's going to predominate. It's going to be this is will be the kinetic product, right? And it's faster here, and you get this product out. So those were like the initial results with the Noyori catalyst, and here's some other selected examples where you have an alkene here, and this is for the just the asymmetric hydrogenation of alkenes, right? You have a alkene here, 98% EE, and this is the catalyst, right? Look at the steric bulk around those bisoxazoline type uh, structures. So you can see here, this is uh, has a bulky substituent here, and then on this side you got these isopropyl groups, and this is where your chirality is coming from right here, right? So you have a this is sterically very bulky, right? So in theory, the more bulky the substituents are, the higher the enantiomer selectivity should be. That's not always the case, but in theory, that's what it should be, right? So this is hydrogenated here. The hydrogens add to the back face. That's the selectivity. You can see that you can tell that because the methyl group here gets pushed up as it's on a wedge coming out of the screen, and you get 98% EE. Right. Same here with this iridium catalyst. It's a cationic catalyst. Um, and you hydrogenate this alkene at room temperature, 50 bar pressure of hydrogen, and 93% EE, 92% EE for this alkene. And these iridium systems are actually using C1 symmetric ligands right here, right? So not C2 symmetric, but still very high in selectivity. And if you remember when we talked about asymmetric catalysis before earlier, these C1 symmetric ligands were designed by Andreas Faults, uh, and this was published in Science in 2006. All right. So with the ruthenium examples, right? These are again these this is getting into the Noyori catalyst system. It's a little bit different, right? I think I said that back here. This is applicable to the Noyori system, but this is just general. The Noyori system is actually a monohydrogen system. This is for dihydrogen systems. I apologize if I misspoke there, but this model is for dihydrogen type systems. But with the Noyori system, with the ruthenium binap, again here you are setting two stereo centers by taking a tetrasubstituted alkene and hydrogenating it, which is excellent. Um, the mechanism is shown here, right? So here the acid on your alkene is acting as your chelating, your Lewis base. It's gonna chelate to the metal, right? And then the metal already has an acetate group here, so you're gonna kick off one of those acetates. When you add in H2 plus the solvent, you add one hydrogen here, one solvent molecule, and then you lose the carboxylic acid, right? Uh, which is right here, right? So that acid, you lose a carboxylic acid. So the acetate group here can get converted into that carboxylic acid, all right? And then now you're here. And again, this is a uh, one hydrogen or a monohydrogen species, right? When hydrogen does the insertion, you can replace it with another molecule of solvent. So that's the complex that you see here, right? And then in order to get to here, you can actually just displace your start material. You can displace it with another molecule after you do the reductive elimination. You can actually displace that with another molecule of the carboxylic acid, right? So it's a monohydrogen mechanism. It's different from the dihydrogen mechanisms, and it does involve a solvent molecule coming on and coming off that metal center. All right. So this technology can also be applied to uh, carbonyl reduction, right? So you can take the ruthenium binap system and hydrogen gas, and as long as there's some chelating um, atom here, like an oxygen or methoxy or an amine, you can actually hydrogenate the carbonyl. But it happens when you have a heteroatom at the alpha, the beta, or the gamma position. So you can this chain can be one carbon that will be alpha, two carbons will be beta, and then three carbons will be gamma, away from the carbonyl carbon, right? Or the carbonyl, the pi system. And the heteroatom is there to direct the ruthenium binary catalyst to the carbonyl so it can be hydrogenated. And even here you can imagine being able to synthesize alcohols in a single step by hydrogenation. That was a huge breakthrough in asymmetric catalysis, right? Because chiral alcohols are ubiquitous in natural product synthesis, right? You have chiral alcohols all the time when you're doing natural product synthesis. And then with a catalyst like this, with BINAP, you can tune it because you can use R BINAP or S BINAP, and whichever enantiomer of ligand you use, that's going to dictate this chiral center, right? It's either going to be on a wedge or on a dash, R or S, right? So this is when you look at here, if you add in hydrogen and this ruthenium already has two solvent molecules attached to it and two chlorines attached to it. But when you add in the hydrogen, you lose HCl. That's one of the byproducts, and then you end up with this ruthenium binap monohydride system, right? And then you can take that when you add in your substrate, it's going to coordinate like so, right? So you're gonna have this ruthenium complex right here, and again, you have a monohydride. You do your insertion where the hydride actually adds to the carbonyl carbon, and you get to this complex right here, right? Plus H plus, which is going to protonate your alcohol, right? In this case, it's not necessary to do a reductive elimination. The solvent can simply displace uh, the beta hydroxy carbonyl compound, right? The solvent can simply just displace it, and then now you're back to here. And if you add H2, you can get right back to here, right? Add, add hydrogen gas, lose a proton, you can get right back to here. And then again, that's a turnover. So now you're here and you can go back through that cycle again. All right. So with the Noyori chemistry, they developed what's called a quadrant model, and that quadrant model helps to predict the stereochemistry. So this is a X-ray, a simplified X-ray structure of BINAP. You know, if for BINAP, these are actually naphthalene and not just simple benzene rings. They're actually naphthalene rings. Um, so yeah. So here we are. Here we have the phosphine, and then the naphthalene part is there, but it's not shown. Um, and then the quadrant model, right? You can see for here this phosphorus, and these are. Let me take that back. The naphthalene part is removed, right? The, with the the bond between the two naphthalene species. But these are the groups on the triphenylphosphine. Let me go back to here, right here, right? So you can see with BINAP, you have two phenyl groups or two aromatic groups on phosphorus, in addition to the naphthalene backbone. All right. So when you look at here, so the naphthalene part is kind of not there, but these aromatic groups actually are on phosphorus, and that phosphorus is chiral. So you have this aromatic group going back into the page, this one coming out. So with this part going back into the page, this is the bottom quadrant over here, the white part, and that's considered open. So a substrate can occupy that quadrant. Same over here, the bottom quadrant, this phenyl ring is kind of coming out of the page, so that's that. And then this one is going back into the page. So this quadrant, the top quadrant here, is open. And so that's how you can predict the stereochemistry. And this is for S binary, right? So if this is the quadrant for S binary, which is here, then it will be the opposite quadrant for R binary, right? The opposite quadrants would be open. So with R binary, the bottom left and the top right are open. With S binary, the top left and bottom right are open. And that's a way that you can predict uh, the stereochemistry of your product, right? So here, this is one model where you have if you're reacting with S binary, notice the R group here is in that bottom right quadrant, so it's in the open quadrant. And then this is how the hydrogenation takes place, and that's how your ligand creates the cavity or the architecture around the metal to control where the hydride is coming from, right? So here with S binary, you're going to get the S beta hydroxy ester, right? In one step. Keep in mind, a lot of times this is done at room temperature. At you might have to have a little bit, you increase the pressure a little bit, but this is normally done at room temperature with the chiral catalyst. Other ways to synthesize beta hydroxy esters that we've talked about would be like the aldol reaction. That's one way to make beta hydroxy esters. And with that, you need aldehyde, you need a ketone, you need a base. It's done at minus 78 many times. Uh, and so this is a really rapid way to access these same structural motifs uh, using a different methodology, right? So here with the R binary, you can see the bottom left quadrant is open. So the R group is going to be there, and the hydride is going to be transferred here, and then you get your R beta hydroxy ester, right? So that's the model to predict the stereoselectivity for that Noyori catalyst. All right. So these are some examples, and again, here's the quadrant model. You can make the catalyst in situ, meaning have everything just together, all in one pot, 7 grams. Then this is a scaled up reaction. This is actually done at 100 in DMF. But you got 7 grams of ruthenium, 18 grams of R-binap, and then you got a 4 atmosphere pressure of hydrogen gas. And this is a 10 kilogram scale. And notice the enantioselectivity selectivity, 97.1% EE, even scaled up, and at 100. And one of the things about doing reactions at high temperature is that a lot of times you kill your selectivity because the higher the temperature is, the more energy is available. If you got competing transition states, there's more energy available for those two, for a disfavored transition state or a disfavored complex to actually have enough energy to get over a barrier and compete even more with a favorite transition state or a favorite complex. So at high temperature to have this type of enantioselectivity selectivity is amazing. You can also use a different ruthenium with a methyl ligand attached to it, uh, rather than a chlorine. And with this BiFEP catalyst, this is only, again, only at 50 degrees, 5 hours, 97 degree, 97% EE and 100% yield, right? For this hydrogenated beta hydroxy ester, which is excellent. Um, and then over here, rather than having a ester, right, you have a ketone and an alcohol as your the alcohol as your other chelating agent. And here, hydrogen gas, 100 atmosphere, and then ruthenium R-binap. So this is the diol that you would get from hydrogenation of the carbonyl. You get that in 92% EE. And then this is the other isomer, right? Because you can imagine this is racemic. So this is the other isomer of the start material, right? And so you can see the if this is the isomer that comes out after resolution, that will mean that the isomer where the hydroxyl group is on a wedge, which is will be here. Like if this was on a wedge, that's the one you can see right here that actually reacts with the ruthenium catalyst to do the hydrogenation, right? And then after kinetic resolution, you can actually get out the other isomer that didn't react, 92% EE, and then potentially take that and use it for some other reaction. All right. So we're going to stop here. I got a couple more reactions I want to show you, a couple more hydrogenation reactions I want to show you on Monday. And then we'll start thinking about like how to close everything out. Uh, I know we don't know we still got like a couple of weeks left. So we're going to talk about